Hi, we are back, okay, with AC steady state power. Okay, so far we have defined instantaneous power, right? Instantaneous power. Okay, we have defined this one, which is simply V of t times I of t. Okay, we have defined average power. Some book call it real power. Some book call it true power. Okay, which is equal to Vm over 2 or Vmim over 2 cos theta V minus theta I, or equal to Vrms Irms cos theta V minus theta I. Okay. What else did you do? Oh, we did apparent power. Okay, apparent power S, which is equal to Vrms Irms. Okay, and we have power factor, right, which is equal to cos theta V minus theta I. So these are the parameters that we have done in the last two clips or the last two sessions. Okay, well, now we're going to do complex power. Okay, well, this is simply a way to extend the full benefit of phasor analysis to study power in this AC steady state. Okay, so therefore it's like another formula for you, okay, that would include everything about AC steady state power. Okay, so I'm gonna start. Okay, so let somehow, I think this is very big, but it's let it be that we have a phasor V equal to Vm angle theta V, and we have phasor I equal to Im theta I for current. Okay, the formula for complex power, okay, complex power is, it's like vector S. Okay, vector S. So I've written S with a bar on top, but if in the book, in the textbook, it's denoted as a very bold black letter S. Okay, and complex power S is equal to a half phasor V times phasor I conjugate. Okay, or if you write it in terms of RMS values, it's equal to phasor V in RMS values multiplied by phasor I in RMS values conjugate. So this is the formula for complex power, and the unit is var, volt ampere. Okay, so the apparent power then is nothing but the magnitude of the complex power. Okay, so that's it. So what is this conjugate, right? So if we said I is equal to the current I, phase I is Im angle theta I, then I conjugate is equal to the magnitude Im, and the angle is changed to minus theta I. So therefore, or IRMS conjugate would be IRMS and the angle minus theta I. So if I apply this to the complex power formula, which is phasor V in RMS multiplied by phasor I in RMS, it would give me Vrms, right, theta V multiplied by Irms minus theta I. So you will get the complex power to be VRMS IRMS, the magnitude, right? And the angle is theta V plus minus theta I. So it becomes theta V minus theta I var. So this is your form of complex power. See? And of course, this is your apparent power. Now, the interesting thing is, next, okay, is that you know that if we write it in this form, this is sort of like a polar form, right? Polar form. It has the magnitude, the amplitude, the magnitude, and the amplitude here, and the phase angle in polar form. So it's part of one form of a complex number. Another form of complex number is of course in the exponential form, right? So therefore we can also, so if we write like this, VRMS IRMS angle theta V minus theta I in polar form, it can also be expressed in terms of exponential form as VRMS IRMS e to the j theta V minus theta I. Correct? And if you use Euler's identity, okay, it means that we can write this complex power as VRMS IRMS cos theta V minus theta I plus j VRMS IRMS sine theta V minus theta I. Wow. See what happened? Is that? Look, is this look familiar? VRMS IRMS cos theta V minus theta I is the real part of the complex number. And it's nothing but P, your average power, or true power, or real power. And the unit is what? Right? Then you have this extra one here, the imaginary part. So P becomes, the average power is the real part of the complex power, okay, which is the average power. This term here, okay, this term here, excluding the j, sorry, let me write it, j like this. This term is called Q. It's the imaginary, so Q is the imaginary part of the complex power. And it's called the reactive power. The reactive power. Okay. The unit of the average power is what? The unit of reactive power is var, volt ampere reactive. Volt ampere reactive. So there are two parts of it, right? So the complex power can be written as P plus JQ. But the unit of the complex power is var. It's very interesting, no? Okay. So that's that. Okay. Well, the complex power not only can be expressed in terms of the real part and imaginary part as P plus JQ. Okay. There's also a formula that can be expressed in terms of the impedance. Okay. So the complex power can be expressed in terms of the impedance. So if we define our impedance as equal to phasor V over phasor I equal to Vrms phasor form over Irms in phasor form, or equal to Vrms over Irms, okay, angle theta V minus theta I, then your complex power can be expressed as the magnitude of Irms square multiplied by the phasor Z, or equal to Vrms, the magnitude of Vrms divided by Z conjugate, okay, phasor Z conjugate, and equal to, and of course equal to Vrms Irms conjugate. So these are the all of the complex power term formulas. okay, so there it is. So in conclusions, so complex power, it's like it tells you everything about the AC power. Okay, so back to complex power equal to P plus JQ, right, where P is equal to Vrms Irms cos theta V minus theta I, Q is equal to Vrms Irms sine theta V minus theta I. Okay, now this is of course average power, true power, or real power, all three names, and this one is called the reactive power. The unit watt, and this unit is var. Okay, so the difference between P and Q, okay, is that P is the average power, okay, or true power, okay, that would sort of deliver to a load and its useful power. Okay, so P is average power in watt, okay, delivered to a load, okay, and this is the useful power. Okay, whereas Q, okay, well Q, okay, well Q is a part that, well, the P average power, it's a power that pretty much consumed or consumed by resistors, where the reactive power, it deals with the power in our capacitor or inductor. Okay, so in inductor and capacitor, Q is pretty much the rate at which an inductor or capacitor store and return energy. Okay, and pretty much the reactive power doesn't really represent any energy loss due to conversion to heat. Okay, same as a capacitor. Okay, whereas the real power or average power, okay, in case of the inductor or a capacitor, okay, ideally all energy stored by an inductor, during the so-called positive portion of the power cycle would be returned to the source during a negative, portion of it. So there's really no net energy is supposed to be lost to do the conversion to heat in the inductor or capacitor. So that's why the true power is zero in the capacitor or inductor. Okay, maybe there is some loss for the inductor, maybe there's some loss, from the winding of the, winding resistance. But it's very small. We consider it's very small and negligible. Okay, so therefore we would say that, that's why the average power in the inductor or capacitor is 0. Okay, so we would deal with only Q, which is consider it to be the measure of the energy exchange. So Q is a reactive power. Okay, and it is which is the rate at which a capacitor or an inductor store and return energy or return energy. Okay, it's a measure of, or in another word, it's a measure of the energy exchange. Right? Exchange between what? Okay, exchange between the source and the reactive part of the load. Okay, and we can say that if Q is equal to 0, okay, that means your load is simply a resistive load. So PF is equal to 1. Okay, if Q is less than 0, your Q is less than 0. Okay, right? That means you would have a capacitive load. Okay, so you have leading PF. Okay, and if your Q is greater than 0, it's the other one. So for inductive load or lacking PF. Okay, so this is all you need to know about the complex power. Right? Now, next one, I would talk about what's it called, the power triangle. Power triangle. Okay, so it's another way for you to remember, and represent the form of the apparent power, real power, and reactive power. By remember this right angle triangle shape. Okay, so right angle triangle, you have one corner as the power factor angle, theta V minus theta I, right? And just remember that the hypotenuse is the apparent power. S equal to VRMS IRMS. So remember that, and of course then you can use your trigonometry skill. You still remember it, right? That on this side then the opposite of the angle, okay, is sine. So you would have this side would be VRMS IRMS sine theta V minus theta I, which is nothing but your reactive power Q. Okay, so this is your reactive power, and the unit is var, right? And here at the adjacent side, right, it's cos. So this is VRMS IRMS cos theta V minus theta I, which is your real power. Okay, and the unit is watt, and this unit is var. Okay, so this is another way for you to remember your so-called AC power formula. Right? So let's look at some example. Okay. So let's say that we have a load here. We have a load here, and there's of course a voltage drop across this load here, and the currents going through this load here, Z. Okay, where V of t is equal to 60 cos omega t minus 10 degrees volt, and the current I of t is equal to 1.5 cos omega t plus 50 degrees amps. Okay, then the question is number A, not number A. Find the complex power and apparent power. Find the complex and apparent power. So therefore, again, it's just a formula you have to remember and know. So complex power is the vector S, right? Written as vector S, and the formula is VRMS, phasor VRMS multiplied by IRMS conjugate. So therefore, it's equal to, right? Oh, the phasor form of the voltage function would be 60 over root 2 angle minus 10 multiplied by 1.5 over root 2, make it RMS values, and the angle is, of course, I is 50, but we have to do conjugate, so it becomes minus 50. So therefore, it's equal to, it becomes, the answer is 45 angle minus 60 degrees var. Well, the apparent power, this is complex power. The apparent power S is nothing but the magnitude of the complex power, which is 45 var. Next questions. Find the real and reactive power. Find real and reactive power. Okay. So you have to know that, well, real is, of course, P, right? And reactive power is Q. So from the complex power formula, 45 minus 60 degrees var, right? It can be written as 45 cosine minus 60 plus J 45 sine minus 60 degrees, right? It comes from 45, sorry, right? It comes from VRMS, IRMS, cos theta V minus theta I, plus J VRMS, IRMS, sine theta V minus theta I. And VRMS, IRMS is the apparent power, which is 45 var. So you would get, so therefore you will get, it's equal to 22.5, right, minus J 38.97 var. Oh, of course, you have to write like this. So therefore, okay, P is equal to 22.5 watt, right? And Q is equal to minus 38.97 var. Real part and reactive part. Okay. You can even get this answer here by simply convert 45 minus 60 degrees in polar form, and this is in rectangular form. So you can use calculator to simply convert the polar form into the rectangular form right away, and you know that, well, the one in the front, the real part is the average power, and the imaginary part is the reactive power. Okay. Next questions. C. Find the power factor. Find power factor and load impedance. Okay, so therefore PF is equal to cos theta V minus theta I, and is equal to 0.5. Leading or lagging? Leading or lagging? Well, sorry, I should express it further. So it's cos sine of minus 60 degrees, right, equal to 0.5. Leading or lagging? Well, the angle is negative, so therefore it's capacitive load, so leading. Okay, and the value of the impedance Z is nothing but phasor V over phasor I, so equal to 60 over minus 10 over 1.5 angle 50, so equal to 40 minus 60 degree ohms, or if you convert it into rectangular form, you will get 20 minus J 34.64 ohms. So that's the answer. Okay, all right. Another example. Okay, let's go another example before we done with power, formula for power. So second example, we have a load Z, right, and it draws 12 kVA, and with the power factor of 0.859 lagging from a 220 volt RMS source. Okay, and we have to calculate the following. Okay, so it means that, well, you have a load. Okay, you have a load, and it's supplied by 220 volt VRMS, and this load here, the specification is 12 kVA, PF equal to 0.859 lagging. So the problem is given you these informations. Okay, so now you have to find the average and reactive power. The average and reactive power delivered to the load. Okay, let's see. First of all, you have to know what's given to you. Okay, you know that this power here unit is var. It is var. So you have to associate this unit with certain power, and of course it is the apparent power. Apparent power. Okay, well, you know PF. Okay, we can find it about it. Okay, so you want to find the average power, right? And the average power is, the formula is VRMS IRMS cos theta V minus theta I. Okay, so you know that this is your apparent power, So it's S times cos theta V minus theta I. And you know that this is, power factor. So it's actually S times the power factor. Oops. So S times the power factor. It's average power. So S, we know just now is 12K. Multiplied by power factor is given, right? The cos theta V minus theta I, 0.859. So the average power, use your calculator, it's 10.272 kilowatt. Now Q is VRMS, IRMS, sine theta V minus theta I. Sorry. So this again is your apparent power. But sine theta V minus theta I, we don't know the values. Okay, so we have to find it. Okay, so you have to find theta V minus theta I. Where can I get these values? Right? So of course, you know it, one formula that involves theta V minus theta I, which is, we know that cosine theta V minus theta I is equal to 0.859. So therefore, the angle theta V minus theta I is simply inverse cos of 0.859, which is equal to 30.8 degrees. So therefore, your Q then is equal to the 12,000 var multiplied by sine 30.8 degrees. And the answer should be equal to 6.144 kilo var. So this is your Q, your reactive power. Okay. Second question is, we want to find the peak current, or the current that go through this load. So let's see, what do we know? Okay, so we know that now, since we know P and Q, we know that our complex number can be written as 10.272, right, plus J 6.144 K var. Correct? So therefore, and we know that this is equal to VRMS, right, IRMS conjugate. So therefore, my IRMS conjugate would be equal to the complex power divided by our VRMS. So therefore, right, it would be, you can do it 10.272 plus J 6.144 K, both K of course, okay, divided by 220, 0 degrees. Or, in other words, is use your calculator, right? It's 12,000 angle 30.8 divided by 220 angle 0 degrees. So therefore, your IRMS conjugate is equal to, turn out to be 54.5 angle 30.8 degrees amps. So your IRMS, right, is equal to 54.5 angle minus 30.8 degrees amps. But you need to find the peak current. The peak current, this is still RMS value. So therefore, the peak current is IM. Okay, so IM is square root 2 of IRMS. So therefore, equal to 77.07 amps. Last questions. What is the load impedance? right? Load impedance. So load impedance, well, it's simply equal to VRMS divided by IRMS. So equal to 220 0 degrees divided by 54.5 angle minus 30.8. So equal to 4.04 angle positive 30.8 degrees ohms. And the angle is positive, so therefore it's inductive load. Okay, it's an inductive load. Okay, so that's it. Some of the example. Okay, about AC steady state